Here's an example involving population. The population of a town with a 2016 population of 90,000 grows at a rate of 2.4% per year. In what year will the population reach 120,000? Well, since this is a population growth example, we have our main equation for exponential growth, y equals y naught e to the kt. Remember, y is the new amount, y naught, y sub 0 is the initial amount. K is the rate constant, and t, of course, is time. And we have two different formulations for the rate constant. For growth, it's natural log 1 plus r, and for decay, it's natural log 1 minus r. And this should be enough to get us through the exercise. Well, this example is certainly population growth, so we'll use the plus version of this. And let's start putting things in. See what we have. So we start with a population of 90,000. That's going to be our y naught. And we're ending with a population eventually of 120,000. Okay, there we go. E to the k. Well, our k in this case, let's do this off to the side. The k is natural log 1 plus the rate, which is 0.024. Remember, you have to move that decimal place 2 to the left. So k is natural log 1.024. All right, so bring that into our e here. So we have e to the natural log 1.024 times t. And if we go back to the wording of our problem here, it says in what year, right? So it's asking us to solve for time. That's also clear from the fact that t is the only variable left in our equation when we're solving here. So let's solve for t. Let's see, we have 120,000 divided by 90,000. All right, we're just doing some algebra at this point. Note that when you're dividing things with a bunch of zeros like that, you can essentially cancel the zeros. All right, so really this is 12/9, which is actually 4/3. Okay, so we have 4/3 equals e to the natural log 1.024 t. And then anytime we have a variable trapped up in the exponent, we can take the natural log of both sides, or the log, really any log. Natural log is certainly the best in this case, to get it down. So that brings the entire exponent down. So we have natural log 4/3 equals natural log 1.024 times t. And then natural log of e is just 1. So that cancels out. Finally, we solve for t. T then is natural log 4/3 over natural log 1.024. Run that through a calculator and we get about, let's round it to one decimal place, 12.1 years. So you can imagine this would be very valuable information for someone like a city planner to have. How long is it going to take the population to grow from 90,000 to 120,000? Is it going to be 2 years? Is it going to be 50 years? You know, in this case, it's going to be 12.1 years. That makes a really big difference on how this town deals with its infrastructure, its transportation, all that stuff. So these are very valuable calculations. So there's an example with population increase. Let's try an example with population decrease. This one is about China's population. China's one-child policy was implemented with a goal of reducing China's population to 700 million by 2050, from 1.2 billion in the year 2000. Suppose China's population then declined at a rate of 0.5% per year. Would this rate of decline be sufficient to meet the goal? Okay, well, this is a decreasing population. We have the same starting equation for exponential growth or decay. It's a nice equation because it fits so many different scenarios. And now we'll use our decay constant here. K equals natural log of 1 minus r. Note that we're looking at the time change from the year 2000 to the year 2050. So we have 50 years that we're working with here. So this gives us our time, t, that's kind of nice. 1.2 billion, so we'll just use this as 1.2. That'll be our starting population, so that'll be our y naught. And we have our k here as natural log of 1 minus 0.05. Again, we convert that, actually it's 0.005, isn't it? 0.005 because we need to move the decimal 2 places to the left. So 1, 2 gives us 0.005 for our rate. Well, this simplifies down to k equals natural log of 0.995. Okay, I think we're ready to start plugging things into our equation here. We don't know what our new population is going to be, but whatever it is, we're going to see if that was enough to reduce China's population to 700 million. So y is going to be our new value. We started with y naught, which was 1.2. We'll just do this all in terms of billions. E to the natural log 0.995 times t was 50 years. And note again that all of this is in billions. When you have something like this, it's much easier to just keep it as 1.2 and remember that we're working in billions than to write it out like as 1.2 billion with a ton of zeros or scientific notation or something. Okay, run this through a calculator. We get about 0.934 billion, which is about 934 million. So that's how many people are expected in China in 2050 based on this model. But remember, the goal was to reduce the population to 700 million, and we're down here at 934 million. So the answer to their question is no, it's not sufficient. Maybe they need the population to decline at a rate of 0.6 or 0.7% per year, 0.8. We could easily do this calculation by solving for r, but we'll save that for another day.